All right, here we go. Today's Wednesday. Sorry I'm not there. My 3-year-old was sick with a fever, so I'm having to stay home with her. But I need to make sure that we get through the things that we need to get through today before you take your quiz at 9:15. So as you're watching this video with your partner or with your group, feel free to pause it as I go and do a problem or two, but don't try to do all the problems on every page or you'll never get through the whole video, and you need to finish the entire video before you take the quiz. So you've only got about an hour to do that. So let's make sure that as you stop along the way, you get to the end of the video and then work back, talk amongst your groups to make sure that everybody is good on what's going on. You need to make sure by the end that you're good with functions and domain and range, because that possibly could be on the quiz today. We're not going to do the warm-up today, although I did think that this question was pretty cool and don't know the answer to it. I would have had to Google it myself. So let's move on. We're going to start today with literal equations, which is where we ended yesterday. Remember, those are just equations with multiple variables. They're done just like we do our normal equations where we're solving for one variable, except now we have a bunch of variables and we're still just isolating those variables using inverse operations. So yesterday we were working through one-step problems. I'd like to do this one at the bottom here where it says solve for C, because we didn't see an example of this, but it's super simple. If I'm trying to isolate C, if it was all by itself, that means I'm trying to get rid of minus S or negative S, and I can undo minus S by just adding S to both sides. So if I do that, minus S and plus S go to 0, which means that I'm left with C is equal to M plus S. So the idea here is we're just using inverse operations to isolate that variable, get all by itself. Those were one step, but we've got to step up our game and move on to a multi-step problem. So with the multi-step problems, again, it's just the same thing that we were doing before. You're just trying to isolate the variable. Here's some helpful hints. I like to think of doing PEMDAS backwards, meaning you do addition and subtraction first, then you do multiplication and division, then you try to take care of the exponents and the parentheses last. That doesn't always work out that way. You just need to be very careful that if you do something to one side, you do it to the entire other side. You can also remove fractions by multiplying by the reciprocal. Remember, the reciprocal of fractions is something like just flip the fraction. The reciprocal of 3/2 is 2/3, and if I multiplied those things together, I would get 1, which makes the fraction go away. Last step usually is to divide by whatever is next to your variable. Normally, what's next to the variable is a coefficient. Well, in this case, it might be variable. So we're going to do a couple of these questions. Specifically, we're going to start with number 9, and it's just a couple of steps. So let's go through here. Let's see. We're going to solve for H, which means I've got to try to isolate that letter H. As of right now, I've got 1/2 times B times H. So if I want to get rid of times 1/2, it really is hard to divide by 1/2. So that's where this multiplying by reciprocals comes into play. If I want to get rid of 1/2, I can multiply by its reciprocal, which is 2/1 on both sides, which is just multiplying both sides by 2. 1/2 times 2/1 is really just 1, and I'm left with B times H on this side. On this side, 2 times A is just 2A. And last step, boy, my H and my B really look alike. Let's fix that H. Sweet. Last step, that's still, again, multiplication. So I can divide this by B on both sides, and those B's go away, and I'm left with H is equal to 2 capital A all over B. Hopefully you're good with that. Let's move on. I'm going to go ahead and do number 11 as well. And again, remember, we're trying to work kind of backwards in PEMDAS here. So if I'm solving for M here, right, the first thing that freaks me out here is I don't like this divide by 2. So since it says divide by 2, I know that I can undo dividing by 2 by multiplying by 2, which is kind of the exact same thing that we did on the last question. So if I multiply by 2, those 2's go away, and I'm left with M times V squared on one side, and 2 times K on the other side is 2 times capital K. Last step, I'm trying to get M all by itself. That's M times V squared. So if I just divide by V squared, then those V squareds will go away, and I'll be left with M is equal to 2K divided by V squared. Good. We'll do one more example of multi-step literal equations, number 13. And on number 13, we are solving for W. So I'm trying to get this W all by itself. Now, here's where if you followed the regular order of PEMDAS, you'd be thinking, oh, that's 2 times W, so undo that first. But If you look up at the hints, I said to try to do PEMDAS backwards. If you do that, then you try to get rid of the addition or the multiplication first. So since I'm trying to get things away from this term, I'll try to get rid of the plus 2L first. I know that I can get rid of plus 2L by subtracting 2L on both sides. This goes to 0 here, and I'm left with P minus 2L is equal to 2W. Good. Now, again, I'm still trying to isolate W, and that is 2 times W. So to get it by itself, I need to then divide by the thing that's attached to the variable, which is the last hint I gave you up top. And these 2's will go away, and I'll be left with W is equal to P minus 2 times L all over 2. And you can leave it just like that. Cool. So that's a quick little refresher on multi-step problems. If you have a couple of minutes, I'd like for you to go ahead and try to solve number 15 and number 17 real quick. I'll let you pause the video real quick, take just a minute or two, try to solve those two, and we'll come back. All right, if you pause the video and finish those two, I'm going to flip ahead and show you the answers to number 15 and number 17. So that's the way you should have done number 15 and number 17. X is equal to y minus b over m, and f is equal to 9/5 c plus 32. Cool. If you want to look at those, you can pause it, and I am going to move on. The next thing should have been the piece of paper that the sub handed out to you today. First thing is just a whole bunch of definitions that I think is going to be really helpful for you to have in your notebook. So anytime you get stuck on what a word means, you can flip back to this. This was a section where we probably would have written this stuff down, but instead I just printed it for you in the interest of saving time. So I'm going to go through these real quick. Just understand that as you hear these words or as I ask you questions on quizzes and tests about these things, you can always flip back and look at the definition and make sure you're good. I have the ones highlighted that I've got to be made sure we're good on today. So relationships and functions, or relations and functions, is what we're working on. These are pretty basic things, the things that you've heard of before. So the coordinate plane is just formed by the intersection of two number lines, the horizontal number line, which is the one that you're used to, and the vertical number line. So it's a horizontal axis and a vertical axis. And the horizontal axis is the one that we call the x-axis. That's this one. It's my x values starting at 0 in the middle. Positive values are to the right. Negative values are to the left. The y-axis is just the vertical axis. That's the one going straight up and down. And again, 0 is in the middle. The positive numbers go up, negative numbers go down. So that creates our coordinate plane for which we can graph different things. So in that coordinate plane, we have quadrants, which are 4 regions in which the x and y axis separate the coordinate plane. We always start with the first region in the top right because that's positive in the x direction and positive in the y direction. And then the coordinates actually rotate counterclockwise. In math, we rotate counterclockwise. So you'll see the first coordinate, second coordinate, third coordinate, and fourth coordinate there listed in Roman numerals. The origin is a super important point. It's the point in which the x and y axis meet, or more importantly, it's the ordered pair of the coordinate 0, 0, where x is equal to 0 and y is equal to 0. Cool. Here's a big thing. We call this an ordered pair. An ordered pair is just a set of numbers of coordinates that are written in the form x, comma, y, meaning whatever that first number is my x value. It tells me how far to go left or right on a graph. And a y value is going to be my output, which tells me how far to go up or down. Good, because the x-axis is left and right and the y-axis is up and down. So I can find any point on a graph by using these ordered pairs. Cool. The x value, or the x coordinate, is the value of the ordered pair that talks about the horizontal placement. That's how far you move x and left and right. And then the y coordinate is the y value of an ordered pair. It's just how far you move up and down. We've got 2 words here that are going to come up later, discrete and continuous. A discrete graph is just a graph that you don't connect the points, and a continuous graph is a line or a smooth curve where you do connect the points. So when we're talking about these 2 terms, what we're really asking ourselves is, do I connect the points? Okay, that is the question that we're asking when we're talking about whether or not it's discrete or continuous. That will come up again later, and we'll deal with more of that as we go. So let's get into the meat today because we're really talking about relations and functions. A relation is just a set of ordered pairs. Now that word set is a big deal. Ordered pairs are all just points that are on a graph, x comma y. So it's a set or several of those ordered pairs. We're always going to denote a set with curly brackets. You can see the curly brackets over there to the right. These little curly brackets are going to tell me this is a set of these three ordered pairs. So 1, 2, 3. Good. Each one of those is a point on the graph, and that's just a set. We call that thing a relation. Now, in that relation, we have what's called a domain and a range. The domain is going to be the set of the x values or the inputs of that relationship. So if I were looking at that set of three ordered pairs over here on the right, the domain is all the x values, which is all of the first numbers, because in my ordered pairs, the x values are the first number in the ordered pair. So you can see the domain is just a set, again, curly brackets, of all three of those x values. See how those three x values come straight from those 3 points. Good? Makes sense? So domain is really, most importantly, it's going to go with the word input, which we'll talk about a little bit later. So set of inputs. Cool. Range is the exact opposite. That is the set of the second numbers of the y values of the ordered pairs in a relationship. So it goes with the term output. So we input x, output y. So when I talk about range, I'm talking about all the possible y values, which is the second value in my ordered pairs. And you'll see again here, it's a set. So we denote it with curly brackets of all of the possible y values. And you'll see again, the y value is lined up there with all those. Cool. So that's domain and range. You'll need those for today. We have this thing that's called a mapping. It allows us to show all of the elements in the domain, all of the elements in the range, and connect them for the ones that go together. So for example, up here in this point, -1 is in the domain, 4 is in the range. So we would take -1, which is in the domain, 4 is in the range, and connect them with a line showing that the input of 1 gives me an output of 4. Sweet, we'll do that through the thing. We can use mappings to tell whether or not things are functions, and that brings me to the big word here, which is a huge thing in math, and it's called function. And a function is a relation in which each element of the domain is paired with exactly one element of the range. Okay, so each element of the domain, I told you domain was inputs, but most importantly, domain went with x values, has to go with one element of the range, which is y values. So for every one of these elements that's in the domain, I can only have exactly one y value. Cool. The way you check this with a set of ordered pairs is you see if any of the x values repeat. And we'll get to that in just a minute when I teach you about functions and trying to see all the different ways to tell whether they're functions. But the x values do not repeat. It would be okay for the y values to repeat as long as every single x value only had one y value as an output. Good. All right, we'll get to that definition a little later. There's more that are highlighted here. You have function notation. We'll get into that the rest of the week. Function notation is a nice, neat way to name a function that's defined by an equation. We're basically just replacing y in this equation where it says y equals 3x minus 8, and we're replacing with f of x, which means that this thing is a function of the input of x, or function of the variable x. And that's function notation. We'll get into that more. Now, I already used these two words, input and output, but they are super good. So input is a value that would be substituted in for an x value into a function. So this x value is what we're inputting in, and then we're actually literally inputting it into the equation to try to figure out what our output is. Well, then that gives us the output. The output is the result of what happens when I substitute that thing in. So if I put the 4 in there, the output is what I get out after I go 3 times 4 minus 8. So one way to say a function, I'm going to say later and over again, is every single input can have only one output to be a function. All right, lastly, and we'll deal with this today, we have the vertical line test. The vertical line test is just a quick, easy way on a graph for us to tell whether or not something is a function. It says that if a vertical line passes through the graph of a relation no more than once, then it is a function. Well, what's easier to tell is if a vertical line passes through a graph more than once. Everybody see how this passes here and here and here, that vertical line? It crosses that S, then that's not a function. Cool. You got a couple other definitions on here, zeros and a couple of sequences things, and we'll deal with those as they come up. But as of today, we don't really need that. Good. All right, so continuing on the next page that the substitute gave you, let's talk about functions. So we've got a definition of a function here. A function is a special relationship between between values. Basically, the most important definition that you could have here, and I'm going to start in red and give you just a minute to write this, is every input has exactly one output. What it means is every single x value can have only one y value. What it means is every single element of the domain can have only one element of the range. So again, every input has exactly one output. So if I was looking at a set of ordered pairs, and by set of ordered pairs I mean a relation. So I'm trying to um, see what relation is, and I have a set which is denoted by curly brackets, and I have all of these coordinate pairs. So you got 0, 6, you got 5, -2, you got 7, 9, and you got 11, -1. I could tell whether or not this was a function simply by just seeing if I have any repeated x values. If I have any repeated x values, then it's not going to be a function. So here, the input of 0 has only one output of 6, and the input of 5 has only one output of -2, and the input of 7 has only one output of 9. And then the same thing goes on the other side, except if I wanted to see a relation that looked like it was not a function, I have a set of these ordered pairs. So let's do them. I have -4 and 1. I have -1 and 7. I have -1 and -2, and 5 and 6. So I have those 4 ordered pairs in this relationship. But as you can see, I have 2 x values or 2 inputs that give me 2 different outputs. So I can't input -1, get 7, and input -1 and get -2. In order to be a function, every input has exactly one output. So every x value can only have one y value. Since I've got repetitive x values there, then that means this is not a function. So to determine whether a relationship is a function or not, when it's looked at sets, all I have to do is look at the x values. If I want to know if it's a function, do I have any repetitive or repeating x values? So I'm going to highlight all the x values. All of those are different numbers. So because I don't have any repeating x values, then the answer to the question, is it a function, is yes. Same thing in number 2. I'm just going to look at the x values. I'm going to highlight them all, -2, 0, 2, 3, and 2. And oh, look, I have a 2 right there. I have a 2 right there. That means this is not a function because I have a repeating x value. You got an input of 2 that has an output of both -4 and +4. Cool. That should be pretty simple. I'm going to fly through these because they're really easy. So to tell down here, you just look at all of the x values. Here again, I have a repeating x value of -3. I can't be a function, input -3 and output -1 and -2. So this is not a function, no. Good. And last but not least, check all your x values here, 1, 2, 3, 4, and 5. Those are no repeating x values. So yes, this is a function. So looking at a set of ordered pairs like that inside curly brackets is one way to represent a function. Another way we can represent a function is in a table. And this is no different than the set of ordered brackets, set of ordered pairs. Except that now I'm listing my ordered pairs in a table, and you should see that first ordered pair looks like 3, 5. So again, to see whether or not it is a function, all I have to do is check the x values and see if I have any repeating x values. And if I do, then that means I have an x value 3 that outputs both 5 and 3, which means no, this cannot be a function. And continue that idea. And all of these are my x values. I don't have any that repeat there, which means that yes, this has to be a function. We'll do the same thing in number 7. You just check the x values. If you have any x values that output more than one value, then it can't be a function. Since I don't have any repeating x values here, then yes, it has to be a function. Good. So if you want to, you can do 8, 9, and 10. It shouldn't take more than a second. I'm going to move on to a mapping, which is another method of representing a relation. These things are the same thing. It's just an ordered pair. The way you would read this is you would take the number -3, which is my x value. It has an arrow to 0, which is my y value, which means that that ordered pair is 3, 0. Sweet. So all of my x values are those ones that are in the domain on the left, which are -3, 1, 2, and 4. And out of each of those, there is exactly one output. See how each one of them only has one output coming out of it? That's easy. That means, yes, this is a function. So if I look over at number 12 and I look at my x values again, or my domain, you'll notice that this number -1 has 2 outputs coming out of that. Literally is one input that has 2 outputs, or one element of the domain that has 2 different elements of the range. Well, that's literally the definition of not being a function. Cool. Last but not least, we'll do number 13. And again, I have 4 different elements of the domain. Each one has only one number coming out of it, or one output. So every input has only one output, which means, yes, this is a function. Cool. All right, let's move on. Flip to the other side. Another easy way to test whether or not something is a function is called the vertical line test. When given a graph, the easiest way to test this is a vertical line. And what it means is, if you can draw a vertical line on the graph that intersects more than one time, then the graph is not a function. I'm going to highlight that. So as you write this down, if you can draw a vertical line that intersects a graph more than once, then this graph is not a function. So to give you a little picture example that you can draw on here, if I were to draw a coordinate axis and I were to draw a graph, let's say we draw the graph, looks like this red line right here. Is there a vertical line that I can draw? So like this blue vertical line, can I draw that blue vertical line anywhere on this graph? See, as I shift it back and forth, where it crosses that red line more than one time? And the answer to that is no. So this is yes, it's a function. Good. So an example of a non-function, let's draw another coordinate axis. And this time we'll say our graph is actually a circle. I'll go with that. So the question is, can I draw a vertical line, vertical being straight up and down, where when I move that line, it crosses my graph at more than one point? And yes, it should be obvious that right here my graph is crossing at 2 different places. So no, this is not a function, which makes this about as easy as possible. Can you look at these graphs and see if you can draw a vertical line anywhere on these graphs where they will cross more than one point? So I'm able to move my graph, my line around on the iPad so I can show this, but I'm drawing a vertical line. Is there anywhere on this graph where when I move it around, I can connect more than 2 points? And you should see I've got a point here, I've got a point here. Since it connects more than 2 points, no, it is not a function. Everybody good? We're asking the question, is it a function? Sweet. And then we just continue with that same vertical line theory. If I drew a vertical line here, or here, or here, or here, or here, every one of them only crosses at one point, which means yes, this is a function. Good with the vertical line test. Should be pretty easy. Let's buzzsaw through these things. So if I draw a vertical line and I was able to shift that vertical line left and right, is there anywhere where that vertical line would actually cross this function more than one time? And the answer is no, which means if it only crosses one time, yes, it is a function. If you can draw a vertical line that crosses 2 times, you see the vertical line here, it's crossing at this point and this point, then that means no, that's not a function. Sweet. Yeah. After that, I'm going to leave number 18, number 19, number 20, and 21 for you. It should only take you about 20 or 30 seconds to draw vertical lines and see if you can decide if they're not a function or not. Go ahead and pause it now, And when I come back, I'll show you the answers. All right, now that you're done with that, let's flip over. Let's show you what the answers are on 18, 19, and 20 and 21. So what you should see is that's a vertical line with 2 points that it crosses. That's a no. Here, you cannot draw a line like that. Here, the vertical line literally hits all of the points on that graph, so that's a no. And here, it doesn't matter what vertical line you draw, so it should be a yes. So moving on, let's talk more about relations. A relation, again, is just a set of ordered pairs. That set of ordered pairs is going to be surrounded with curly brackets, so then you'll just have a bunch of x and y variables in there. All right, so it's important to note that the set of all of the x values is going to be called the domain. We already talked about that in our definitions. So the domain is all of the x variables or the inputs, and the range or the y values is going to be called the range. It's the set of all of the output. Sweet. So if I were to look at this relation in number one, which is a set of ordered pairs, everybody see I've got the curly brackets. I've got 1, 2, 3, 4, 5 different ordered pairs, so 5 different points. I can list in a set notation, let's do it in blue since I did domain in blue, just with sets, just list all of the possible x values, and that will be my domain. So I'm just going to list all of the x values, which is the first value here. And when I list them, you should always list them least to greatest. That's going to help you greatly when you have to start writing domains and range. So the lowest of those x values is -3. I don't need to list it twice since it's already in there, which since it's in there twice, that should mean that this is not a function. So I'm just going to list the next lowest, which is -2. The one after that is 1, and then 3. So I only have 4 different possible values that are in the domain. Same thing for range. For range, I'm just going to list all of the y values this time. So I'm going to highlight those like I did over here for range with green, and use red to write my set of possible y values. So I got a set, and I'm just going to list all those again, list them least to greatest. So the least or the lowest number of those green y values is -4. The next is 0, then 1, 2, and 5. So the range of this relationship has 5 numbers in it. Oh, we can take that same set of ordered pairs and we can put them in a table and just make sure that each point is your x and your y value. So that first point, I have an x value of -3 and a y value of 1. And then you continue that way. -2 and 0 is my output. When 1 is my input, 2 is my output. When 3 is my x value, -4 is my y value. And when -3 is my x value, 5 is my output. And again, you should say this is not a function because that input is giving me 2 different outputs. And you're going to see it just as well in the mapping. So when we do a mapping, you can either label this one of 3 ways. You can either call this x and this y. You could call this inputs, and you could call this outputs, or you could call this domain, and you could call this range. But in that first circle, you're going to put all of the elements of the domain in there, hopefully listing from least to greatest from top to bottom. There we go, 1 and 3. And then same thing in the range. You're going to go -4, 0, 1, 2, and 5. And then it's just a matter of connecting each one of those things, each one of those inputs with their outputs by going down the table. So the first one, I have an input of -3, an output of 1. So I'm going to draw a line from -3 to 1, and I'm going to continue that idea. Input of -2, output of 0, so I'm going to draw a line from -2 to 0. Input of 1, output of 2. I'm going to draw a line from 1 to 2. Input of 3, output of -4. I'm going to draw a line from 3 to -4. And the last one is the one that makes this not a function. Input of -3, output of 5. So I'm going to draw a line from -3 all the way down here to 5, and that's what's called a mapping. Now to put all this on a graph, I just have to put all of these points on the graph. Remember, your x-axis is the horizontal axis. Your y-axis is the vertical axis. So really, your x-axis is representing all the domain, and your y-axis is representing all the range. So to do this, all you have to do is go left and right, left or right the x value, and up or down the y value. Always start at the origin in the middle. That says -3, which is negative in the left direction. So I would go left 1, 2, 3, and then y is +1, up 1, and I would have a point right there for that very first point in my table. Do the same thing for the second one. That says go left 2, up 0. So you come over here and you start at the origin. You go left 1, 2, and you go up 0. So you should have a point right there. Continue. Left, sorry, since this is +1, we're going to go right 1, and then up 2 since that's positive. So right 1, up 1, 2, and it should have a point right here. +3 in the x direction is right 3. -4 in the y direction is down 4. So I'm going to go right 3, down 1, 2, 3, 4, and I'm going to put a point right there. And last but not least, the one that's going to make it not a function, that's down, sorry, x direction is left and right. So left 3, and up or down, +5 is up. So left 3, 1, 2, 3, up 1, 2, 3, 4, 5. Booyah, right there. Oh, cool. Everybody good with how to put relations on a graph? So what I would do right now if I were you is I would pause this and I'd go ahead and try to do number 2. Remember, domain is the set of all inputs or x values. Range is the set of all outputs or y values. This thing should translate right over here just like points. Remember to try to list domain and range least to greatest. And then when you connect them, go least to greatest top to bottom in here and make sure you only connect the ones that connect. They won't necessarily always go straight across like that. Plot all your points. I'll pause it and show you what it should look like when we're done. All right, hopefully you paused it, and here's what number 2 should look like. And if you pause it right there, you can check your work. That's the domain, that's the range. We got the table, we got the mapping, and we got the graph. And this one, since every single input only has one output, should be a function. So let's move on to the very last page again, and let's continue to talk about domain and range. When we're looking at a graph for continuous graphs, all right, when we talked about continuous, it's lines that are connected. There's no holes in them. For continuous graphs, you can find the domain. Remember, domain is x value. So the easiest way to find the domain is to scan your pencil from, oh, I did it in blue, so let's do it in blue. From left to right and identify the x values in which you are touching the graph. So if I look at number 1, as I start my pencil to the left, that arrow is telling me that my x values are going all the way this direction to -infinity, right? And as I continue scanning this way, my graph is continuing. I'm hitting x values the whole way as I scan across. And these x values, I'm hitting every single possible x value from -infinity all the way until I get to the right, which I have this arrow which is telling me it's going all the way to +infinity. So because of these arrows, my x values are going from -infinity all the way to +infinity. So you could write the domain as an interval. That interval would look like -infinity as my least number, +infinity as my greatest number, and since you can't get to infinities, we would use parentheses since you can't actually get there. So I can represent it as all the possible numbers between -infinity and +infinity. Guess what? We have a cheat way of writing this. You can just call this all real numbers. Sweet. So from now on, when I say all real numbers, it means that my x and right, my graph goes all the way to the left and all the way to the right. Sweet. So range, it says for range, we want to scan our pencil. We'll see range was y values. So we want to scan our pencil down and up and identify all of the x values. Now, the reason why I said down and up in that order is because I told you on the last page to go least to greatest and left to right is least to greatest. Well, on the y-axis, down to up is least to greatest. So if I start way down here, I don't actually get to my graph until I get to this point. So the lowest my graph goes is -2, right? And as I go up, both this arrow and this arrow are going up, and they're going to continue going up, which means this is going to go all the way up in the y direction to +infinity. So the lowest possible value for my range is -2. The highest possible value for my range is infinity. So now the question is, does it actually get to -2? If you see that point actually get to it, then that means it gets to -2, which means it's included and I need to use a bracket. We know that I cannot get to infinity, which means I need to use parentheses. So basically, I've written this in interval notation. Or another way that you could represent this is to say, what kind of y values makes that thing true? Well, it's all the y values that are greater than or equal to -2. Does everybody see how this is interval notation, which we've been working on? This is inequality notation. What it means is all of the values that are above that line, including what's on that line, are where that graph exists. Good? Okay, let's do another one. Again, we're going to scan left to right for domain and range. So if I start all the way out here to the left and I come in, the least possible value for my domain is right there at, what is that, -3. And as I keep going, it's all the possible values in between -3 and my greatest possible x value is 3. So all of my x values, let's do it in blue, all of my x values better be between -3 and 3. That's what it looks like in inequality notation. Does it actually get to -3 and +3? The answer is yes, which is why I have an equal sign underneath that. You can also write this in in interval notation. You just put the least possible value, the greatest possible value. And since it does get to -3, we're going to use brackets on it. And since it does get to +3, we're going to use brackets on it. So either of these notations will tell me all of the possible x values, because this curve right here is hitting all the values for x between -3 and +3. Sweet. And then for range, we're going to do the same thing. We're going to move down to up. So the first value for my graph that starts from the bottom is -3. So that's going to be the bottom value. And then as I climb, I go all the way from -3 up to +3, but this time I'm talking about y values. So it's all the y values that are greater than or equal to -3 and all the y values that are less than or equal to 3. That's everything that's in between these 2 points as a point that's on that graph. I can also write this in interval notation, which personally I think is a little easier. The least possible value is -3. The greatest possible y value is +3. And since it can hit both of those, I'm going to use brackets instead of parentheses. Good. All right, now what I want you to do is go ahead and pause it. I'd like you to try number 3, number 4, and number 5. Actually, go ahead and do number 6 as well. And when you come back, I'll do a quick review of the answer. So pause it. All right, hopefully you took some time to pause that and check it. And now I'm going to flip over and show you the answers to those. Again, on number 3, left to right, this arrow is telling me it goes all the way to the left. This arrow is telling me it goes all the way to the right. That means it goes from -infinity to infinity, and I told you you could write that as all real numbers. Up and down, this arrow is telling me that it also is going up all the way. This arrow is telling me it's going down all the way to -infinity, up to +infinity. That, again, is all real numbers for the range. So for number 4, when I look at how far left and right it goes for domain, or the x values, this arrow is not only going down, it's also going to the left. So this is going to go all the way to the left to -infinity. This is going to go all the way to the right to +infinity because of this arrow. Again, that's all real numbers. When I look at up to down, down to up, which is range, y values, those 2 arrows take my y values all the way down to -infinity. And I go all the way up to this value, and I actually get to it, which is 1, 2, 3, 4, 5. So it goes 5 all the way down to -infinity. That means y has to be less than or equal to 5. You could also write this in interval notation as -infinity to 5. It doesn't include -infinity, and it does include 5. Good? All right. There's a look at number 5 and number 6. If you have questions about this, just email me. And now what I think you should try to do is try to complete as much of these worksheets as you can until 9:15, at which point you'll take your quiz. Good luck.